Okay, we're almost done with this chapter on bonding. I want to get this done this week because we really only have like, what, 5 weeks of school left? And there's one more chapter I want to cover on gas laws. So there's a little bit more about bonding I want to look at, and then we can move on. So today let's look at something called dipole moment of a molecule. A dipole moment is a vector, which means it has a direction to it. It's a directed quantity. So the dipole moment has a certain size to it, and it has a direction it points. That basically describes the polarity of the whole molecule. Now, you'll remember back earlier in the chapter, we looked at electronegativity and how that affects whether you have a normal covalent, a polar covalent, or an ionic bond. Okay? That applies to specific bonds. So if I have a big molecule, each bond individually, I look at the electronegativities and see if it's a polar bond or a nonpolar bond. We'll leave ionic bonds out of this discussion. Dipole moment basically applies that to the whole molecule. All right, so you got all these different bonds pointing in all different directions because now we know about molecular geometry. What does that mean about the overall polarity of the molecule? Sometimes the molecule can end up being a polar molecule, or it could be a nonpolar molecule, or again, somewhere in between, the shades of gray, and that's what the dipole moment is. The bigger the dipole moment vector, the more polar the molecule is overall. Now, it depends on the two, and by the way, the symbol we use for it is mu, although you don't have to worry about calculating this at all. It's just, we're going to talk about it theoretically. And the unit it's measured in is something called Debye, named after a scientist whose last name was that. Dipole moments depend on two things. Depends on the polarity of the bonds, and it depends on the molecular geometry, how those bonds are arranged. If the bonds are all symmetrically arranged, even if they're polar, they can cancel out and give you a nonpolar molecule, which we'll look at it as in a couple of our examples here. If you have nonpolar bonds, obviously the molecule is nonpolar because there's nothing polar there. But also, if you have polar bonds and they're asymmetrically arranged, then you can have a polar molecule. So that's really what you need to have a dipole moment. And again, to speak loosely, we talk about having a polar molecule or a nonpolar molecule. By saying a polar molecule, I simply mean it has a rather large dipole moment. By saying a nonpolar molecule, I say it has a rather small dipole moment. That's vague. How big is rather big and rather small? Well, it kind of is whatever. Again, there's shades of gray in between there. You have a molecule that might be kind of a little polar. So let's look at some examples. I'm going to draw the Lewis structure for these pretty quick because I think we've been through enough of those, and then focus on the geometry and how it affects this. The simplest one, and we'll have to remember all these, or I'll have to come back and look at them, is the O2 molecule. Oops. There, okay. So let's go to my whiteboard here and make an O2 molecule. Remember, we have 6 for each atom, so that's 12 total. 2, 4, 6, 8, 10, 12. I came up short, so I'm going to have to get rid of 2 of these and make a double bond. So the oxygen molecule diatomic looks like that. We've done that Lewis structure before. Now, that bond is a nonpolar bond. So the molecule itself is nonpolar. Or we'd say the molecule has a dipole moment of 0. Or I guess you'd say mu equals 0 for this molecule. Now, that matters because remember, just for example, water molecules are polar molecules. They got those slight plus and negative ends to them. So when water wanted to dissolve something, you'll recall from back in chapter, who knows what it was, 4 or something, whatever. But when water wants to dissolve something, it comes in and the positive side of water grabs onto the negative side of the thing it's dissolving, and vice versa. Well, this molecule, there is no plus or minus side because the only bond is nonpolar. So water molecules have nothing to grab onto here. And therefore, this molecule, diatomic oxygen, has very poor solubility in water, which we know is true. If oxygen was very highly soluble in water, all the oxygen in our air would be dissolved in the oceans, and we kind of have a hard time with that. Another issue is Since there's no plus or minus side to this molecule, it's not really easy for them to stick together. So they tend to fly apart and remain in the gas phase. If these molecules had been polar, there'd be a positive side and a negative side, and then they would stick to each other, and it would likely be a liquid or even a solid at room temperature, which again would be rather difficult to breathe, wouldn't it? So if we look at a similar example, look at the HCl molecule. Oops. Let me undo that and write it the way I can show the bonding easier. Bond, 2, 4, 6, 8 electrons. 7 plus 1 is 8. That's all of them. Now, this molecule, the chlorine has a much higher electronegativity than the hydrogen. Chlorine's electronegativity is, 3 point something. Hydrogen's is like 2.1. So it's an electronegativity difference of around 1-ish. A pretty large difference compared to the 0 over here, which means there's a dipole moment. Notice in this case, again, there's only one bond to worry about, so it's no big deal. Now, the higher electronegative element gets the negative charge. The lower electronegative element gets the positive charge. How we show the dipole moment vector? We put a plus sign on the positive one and then draw an arrow pointing toward the negative one. So the dipole moment vector points to the chlorine from the hydrogen. Okay? So that's how we show it. And again, in this case, notice it's a simple molecule with only one bond. Let's look at the H2O molecule. I know I'm doing them out of order, but whatever. So you have H2O is this, and then lone pair, you've seen this before, which, by the way, makes that a tetrahedral overall geometry, doesn't it? But with only 2 bonds and 2 lone pairs, it ends up being angular. So the actual molecule looks more like this, where the bond angle in there is a little under that tetrahedral angle of 109.5. So the molecule is bent at an angle. Now, that O to H bond is polar. If you go back and look up electronegativities, again, oxygen is 3 point whatever, hydrogen is 2 point whatever, which makes a pretty big difference in electronegativity. So this is a polar bond, okay? Which means the oxygen has a slight negative to it, a little delta negative, and the hydrogen has a slight positive to it. Now, I've analyzed that one bond in terms of its polarity. What about the other bond? Well, the same discussion applies. There's a slight negative on that oxygen right on top of the other one, and there's a slight positive on this hydrogen. Now, notice it's asymmetric. So, look for the average positive. Positive on the 2 H's, the average location of the positive is right here between the 2. The average position of the negative is right there on the O. So the dipole moment vector goes like that for the water molecule. So if I draw a little H2O molecule like that, the dipole moment vector pokes right through the molecule in that direction, from between the H's to the oxygen. Which again explains stuff we talked about earlier in the year. The hydrogen end was the positive end, the oxygen end was the negative end, when we were looking at how it dissolves sugars and salts and things like that. Back in those days, you just had to accept my word on faith. That's the positive end, that's the negative end. But now we know why in terms of electronegativity and bond polarity. The molecule ends up with a dipole moment vector pointing from hydrogen to oxygen. Okay? Now, interesting little note here. Very similar molecule, H2S. Notice all I did is I replaced the oxygen with a sulfur. And so it's going to have the same Lewis structure. 2 lone pairs, 2 bonds, which again makes it overall tetrahedral and arranged as an angular molecule with a very similar 109-ish degree bond angle in between right here. Okay? So the molecule is shaped just like the water molecule is shaped. So you think, oh good, it's a polar molecule. But look at the electronegativities of these. Sulfur's electronegativity is like 2.5. Hydrogen's, like I said, is like 2.1, 2.2, something like that. So the difference in electronegativity here is very small, making it a non-polar bond, no plus or minus side to it. Same for this bond. So in this case, even though the molecules bend at an angle, just like water molecule is, the bonds themselves are not polar, so the molecule itself has very, very little dipole moment. It's going to have a slight dipole moment pointing up toward the sulfur because it's not exactly equal electronegativities. But the dipole moment is going to be extremely small, making this molecule behave pretty much as a non-polar molecule, which means H2S has fairly low solubility in water. H2S molecules don't stick together real well, so they're a gas at room temperature. This is the gas that comes out of rotting eggs, by the way. And so H2O, very similar molecule, same overall shape, has a dipole moment because of those electronegativity differences, and it's a liquid at room temperature. H2S, similar molecule, gas at room temperature because very, very tiny dipole moment. Now, let's look at one more example here. I'll clear my board. And let's look at the CO2 molecule. I'm running low on time, so I won't do the whole Lewis structure, but you've seen this molecule so many times now. There it is. Now, carbon in the middle, there's two pairs on carbon. There's no lone pairs. So this molecule is linear. This shows just like the Lewis structure is, okay? Some of you had this on your quiz. So this molecule is a linear molecule. Now, looking at the bonds, carbon to oxygen is a polar bond, 3.5, 2.5, something like that. So the difference in electronegativity is around 1, which means the carbon has a slight positive, the oxygen has a slight negative. Now, what about the other bond? Well, same discussion. Slight positive right on top of the other one, slight negative here. Now, the dipole moment vector is going to go from the positive to the average location of the negative. But take these two negatives, average them together where they end up being, right here on the carbon. And so the plus and the negative average out to being at the same place. And therefore, there's no direction to the vector. There's no dipole moment vector. The difference between them is 0, so the dipole moment is 0. The carbon dioxide molecule has a dipole moment of 0. It's a very nonpolar molecule. Once again, that means these molecules don't stick together to each other real well, so it remains a gas at room temperature. If these dipole moments had not canceled, like for example, if the molecule were bent at an angle, like water molecule is, then we would have the same discussion as water. The charges would not have canceled, and you'd have ended up with a polar molecule. If that were the case, carbon dioxide would be a liquid at room temperature, and it would be highly soluble in water. As it is, it has some solubility in water, and you'll learn in Gen Chem in college or in AP Chem or whatever, you'll learn why that's the case in terms of something we call polarizability of the electron cloud. But its solubility in water is much, much lower than it would have been in that circumstance. So most of the Earth's CO2 stays in the atmosphere, and only a small amount dissolves in the ocean. If it were bent at an angle, virtually all of our carbon dioxide would dissolve in the oceans instead. Okay, so again, these molecular geometries and the dipole moments that grow out of them matter a lot. They determine the properties of these molecules. If water molecules were linear, you wouldn't exist, because then water would be a gas at room temperature, and you'd have no ocean to dissolve biomolecules in to evolve life on Earth. Okay, a couple more examples. The methane molecule, CH4. Notice those bonds, carbon to hydrogen, have an electronegativity difference of like 0.4. So they're already nonpolar. You don't have to worry about it. It's a tetrahedral molecule. The bonds also all cancel out. Carbon in the middle, hydrogen on either end. Right? So now, it's a nonpolar molecule. What if all these hydrogens were chlorines? Well, now the bonds are polar. I should draw my bonds here. But they still are evenly arranged and they all cancel out. And so it's still a nonpolar molecule. But what if I made just one of these a chlorine? Now you got a polar bond up here and nonpolar down here. Now you do have a dipole moment poking up that way. So this chloromethane molecule is soluble in water, whereas the others were not. We'll stop.